A really powerful tool for integration is integration by parts. And this is the form, right? It says that if you have an integral, we can break it up by doing a substitution for a u value and a dv value, and then we can rewrite it in this way. We'll start by understanding what this form even represents and why, how we know it is true. And then we'll do a few examples. This is a nice tool, but I know for students who are just learning it, it can be very confusing about how to select the substitutions, the u and dv substitution, and then actually how to apply it. So we'll go through a few simple examples, and we'll look at some longer multi-step examples as well. So first, we'll explain why this is even true, why this integral is equal to this form of the integral. And I try to color code this because sometimes the u and the v look very similar, right? The u, at least in this font, has that little tail, but I'll try to color code it in at least the first couple of example problems. So we can rewrite this equation and just look at uv, right? So the product of two functions. And so if we can show that the product of two functions is equal to the integral of the first with respect to the other, right, u dv, plus integral of the second with respect to the first, right, v du, u dv, v du. So what does that even mean? Well, we know that we can take a look at this product of two functions and take the derivative of it with respect to x, and we can use the product rule from a few videos ago. I'll link it in the description. And this would say the first function multiplied by the derivative of the second plus the derivative of the first multiplied by the second function, right? So we know the product rule. So if we write it in this form, now I can integrate both sides, right? You place integrals on both sides. We know the additive rule, so we can separate this full integral into two separate integrals. So I just basically put an integral sign in front of here and took the integral with respect to x, put the integral sign in front of this term here, took the integral of it with respect to x, and same thing for the third term. Now dx, that can cancel out, and I can look at this as the integral of duv. This can be the integral of u dv. This can be integral of du times v, right? And the integral of a derivative is just the function itself. So the integral of duv is just going to be uv. And then this simplified to the integral of u dv, and this to v du. Okay, so simple manipulation of the integral by parts function to isolate the uv products, and then product rule, and then integrating. And now this looks exactly like this form. And if I just move the uv over here, if I just move the vdu over here, then I basically have my initial function. So before we jump into the example problems, I want to show you another form of the integral by parts that you might see, right? So u might be replaced with f of x, and g of x might replace v, right? So in this case, it's saying the exact same thing, right? This says u, so f of x, dv, this is g prime dx. This is basically saying what this is saying right here, dv dx dx, right? Because g prime is dg dx. uv is replaced with fg, vdu is replaced with g f prime dx. So either form is saying the same thing. For the sake of this video, we're going to stick to the u dv form because I think it's a little bit simpler to write out. But if you understand in this form, that's fine. Just work from this. This will just be really the first few steps. So let's take a look at some example problems of applying integral by parts. So to solve our first example problem, it is useful to have our table of integrals and table of derivatives to reference. Now remember, the left side of this equation is our original function, and we're wanting to select a u value and a dv value as a substitution. When we're selecting these, this first example is a pretty, I think, obvious choice, and I'll explain why. But future examples, there's multiple things you can choose. Now, what makes sense to choose as a substitution for u and dv all depends on this integral term, right? So the idea is, oh, I don't know how to solve for the integral of my full function, so I want to use integral by parts, so I can change that integral that I need to take to a simplified form, right? So you got to think, when you select a u value, it's going to turn into a du. You're going to place the derivative of that into this integral. When you select dv, you need to be able to integrate that so that you can select that in here. So we'll take a look and see for the next couple of problems what makes sense and what doesn't make sense, and how. I mean, sometimes there's only a couple options, so you can do a trial by error. Trial and error method, but you'll see a pattern start to arise. All right, so this problem is, I think, pretty apparent what you should select for u and what you should select for dv. Now remember, when you select the dv component, it has to contain your dx term. It has to. It could contain something else in addition to it, but it has to contain the dx. So because of that, it makes sense to choose natural log x as the u value and dx as my dv value. Now, before we actually jump into this, you might look at this and say, oh, I remember taking the integral of natural log in a previous video. No, we never actually did that, right? So we took the derivative of natural log and we solved it, show that is equal to 1 over x, and we took the integral of 1 over x and we show that that was equal to natural log of x, but we never actually took the integral of natural log x. So we said we're going to select u as natural log x and dv as dx. Now again, you could have more terms in front of this dx, so it's not always just this straightforward. You might be thinking, well, why can't I choose u equals 1 and dv equals natural log x dx? Well, that kind of defeats the whole purpose, right? So if you choose dv to be natural log x dx, then when you try to select what your v term is, you're taking the integral of what you don't know how to take the integral of, right? So this makes sense for this problem. Okay, so once you select what you want to try to substitute, the next thing you need to do, so you have u, you need a du. You have dv, so you need a v. So you need to take the derivative of natural log x, which is just 1 over x, and then you need to take the integral of dx, which from here we know is just going to be x. All right, so we got du is equal to derivative 1 over x dx, right? Because it's du dx is equal to 1 over x, so du is equal to 1 over x dx. And the integral of dv is v, integral of dx is just x. All right, because that's just a constant one. All right, so now all we need to do is plug in these into this form. So there's my u, there's my v, that's my product. There's my v, and there's my du. That's my integral function now. So I got uv minus integral v du. Well, v du can simplify to just integral of dx. So I got natural log x times x for the uv part, minus integral of dx. Integral of dx, just like this part here, is just equal to x. So natural log x minus x plus c, because it's indefinite integral, is equal to x natural log x times the quantity natural log x minus 1. Right? So the core of the integral by parts is selecting a u and a dv that can simplify the integral that I need to take. Right? So what's the main thing that this simplified? by choosing u to be natural log x, I removed the natural log function from the integral piece. That's the part that I didn't know how to do, right? And now I do know it, so I can put it in my tables if I wanted to, but this is the demonstration of it. We can also do integral, a definite integral, and let's say from 1 to 2, and all you would need to do is you take this component of your indefinite integral solution and then apply your upper and lower limits from 1 to 2 in this case. So upper limit 2 times natural log 2 minus 1 minus the lower limit 1 times natural log 1 is just 0 minus 1, and we get our integral. And this is the graphical form of it, right? So we're going to repeat this process for another example problem that's slightly more complicated, and we'll keep progressing from there to show a variety of examples. In this example problem, we basically have the same problem, except we have a 1 over x to the fourth added here. Now, if you remember from the previous problem, we chose the natural log x to be my u value precisely because du would be the derivative of natural log. And we knew how to take the derivative of natural log, but we didn't know how to take the integral of natural log. The 1 over x to the fourth, I have a lot of flexibility with this one because I know how to take the integral of it and I know how to take the derivative of it. So I can do a lot of different things with this term, and I feel comfortable. So what we're going to do is we're going to move this 1 over x to the fourth and combine it with the dx term, and that will be my dv. And then we're going to choose u to be my natural log so we can get rid of the natural log in the final integral. So I have my u value, I have my dv value. Now I need to find du and v, right? So for du, I just need to take the derivative of natural log x. So this will be du is equal to 1 over x dx. For dv, I need to integrate this so I can get v. So I integrate 1 over x to the fourth. This is the same thing as x to the negative 4. So that would use n equals negative 4. So I will get 1 over negative 3, right? So 1 over negative 4 plus 1, or negative 1/3, x to the negative 4 plus 1, or 1 over x cubed. Right? So I got my du term, I got my v term right here. And now all we do is plug it in, right? So uv is negative 1/3, 1 over x cubed, ln natural log x, minus the integral of v du. V is right here, negative 1/3, 1x cubed, 1 over x cubed, du, 1 over x dx. So u dv, here's my uv, and here's my integral v in blue du. And we can clean this up a bit. So for this term right here, I get negative 1/3 natural log x over x cubed. That's right here, the uv. For this term here, I have a negative sign, minus, so that's my positive 1/3. I can pull out of the integral because I know the constant multiplier is not going to be affecting anything. 1 over x cubed times 1 over x is 1 over x to the fourth. Okay, so now I can just keep this as is, negative 1/3 natural log x over x cubed, and I can take the integral of 1 over x fourth, so I get 1/3 times the integral of 1 over x to the fourth, which we basically solved for earlier. So negative 1/3, 1 over x cubed, and then plus c because it's an indefinite integral. And then if I want to, I can clean up even more, right? So I can pull out the negative 1/3 x cubed. So negative 1/3 x cubed times natural log x plus 1/3, and then plus c. So we could do that. We can apply definite integral and just plug this in, right? So if we had this integral and then we applied the same limits as the previous problem 1 to 2, I can just take this integral solution, place it there, and apply my lower and upper limits, as we see here, and we find the integral. Right? So the key thing from these two example problems is choosing a u value that I can take the derivative of that simplifies things. The next two problems we'll see we need a multi-step approach. One step won't solve for it, right? Meaning one substitution integral by parts won't solve my problem. And we'll see how we deal with these types of problems. Okay, so for this problem, we're going to need to take a multi-step approach. And so because of that, I am giving us more space, and I'm going to use a different color coding scheme. So just pay attention when we mention u versus v, that the u has a tail. It's not going to be color coded the way we have up here. All right, so our problem is x cubed times cosine x. Now, there's a couple options, right? You can choose u to be cosine x or u to be x cubed. So a couple of things to think about. Well, I know the derivative integral of cosine basically goes cosine, sine, and there's sign changes there. I know that x cubed, the derivative of this, makes it go from x cubed to x squared and like keeps scaling down. Integral of it makes it keep building up. So if I don't know that the integral of x cubed cosine x, I'm going to have a harder time to find integral of x to the fourth cosine or x to the fourth sine x. So that gives me a little bit of a hint of where to choose, right? Because if I choose u to be x cubed, then my du, this x cubed component, is going to scale down. It's going to be an x squared term. If I instead choose the x cubed term to show up in the dv, when I look at my integral, that x cubed is going to turn into an x to the fourth component, right? So that's kind of where I'm looking at the first step of this one. So because of that, we're going to start with u equals x cubed and dv to be cosine x dx. So remember, the first step is just define u and dv. The next step is to define du and v. So if u is x cubed, du will be 3x squared. And if dv is cosine x dx, I'm going to integrate this. So I need to figure out the integral of cosine is sine. So I'll have sine of x. So du will be 3x squared. V will be sine x. All right. Now I can just plug in to my integration by parts equation. So I have uv, x cubed is my u, sine x is my v, minus integral v du, sine x is my v, 3x squared dx is my u. Now you might say, I don't know how to take the integral of this. We don't, but we have changed the x cubed term into an x squared. So I'm going to keep processing this until this term goes away, essentially, and I'll just have a trig component in here. That's the goal. All right, so I can simplify this before we take the next step. So x cubed sine x minus, I pull the 3 out, so 3 times the integral x squared sine x dx. And I put this in red text because I'm going to set up the integral by parts for this section only. And we're going to repeat the process. Now, from the logic of this first piece, what would you choose as u? We chose x cubed as u last time, and we chose cosine x dx as my dv before. So it would make sense, I think, to choose x squared as my u value and sine x dx as my dv value in this next phase. So that's what we're going to do. So x squared sine x dx. Solve for du, which would just be the derivative of this, right? 2x dx, and then integrate sine x dx. So integrate that, I get negative cosine x. So I got du is 2x dx, v is negative cosine x. Okay, and now we just plug it back into this equation. So uv is x squared minus cosine x, right there. And then minus integral v du, v is negative cosine x, du is 2x dx. Okay, so clean this up, we get negative x squared cosine x plus 2, pull that 2 out, integral of x cosine x. And I put this in green because we need to do this process one more time. And hopefully you see the pattern. You choose u to be x cubed before, now we're going to choose u to be x, we're going to choose dv to be cosine x just like we did before. Okay, so du would be what? Dx, and then v would be sine of x, just like we did up here. Now we plug into our uv, that's x sine x, minus integral v du. V is sine x, du is dx, and I know how to take that integral, right? So I get x sine x from the uv term minus integral sine x dx from the v du term. And then I can integrate that. Integral of sine x is just negative cosine x. So I get x sine x minus minus, so plus cosine x plus c. So this term is this green component, and this term is this red component. And so we're going to do substitution right back into our original form. So the original integral x cubed cosine x dx is equal to x cubed sine x minus 3 integral x squared sine x dx. That's what I have here. And then if I plug in minus x squared plus 2 integral x cosine x dx into this portion here, so it'll be minus 3 times that quantity. And then I do one last substitution of this term into this. And so x cubed sine x minus 3 times the quantity, negative x squared cosine x plus 2 times this component, which we solve for in that third step right there, x sine x plus cosine x. All of that plus c because it's indefinite integral. And again, we can do a definite integral to find the area by applying the limits to this final function. All right, so multiple steps, but the process is what I'm interested in you making sure you understand. We have an xq component, and I know I can scale that down if I define that as u, and then every single step it's going to get smaller and smaller, right? From an x cubed, turn to an x squared, turn to an x, and then we finally can solve that final integral. Okay, we'll take a look at another example that's similar to this one, but we have a couple of options. We'll solve it one way, and you can try to solve it the other way. It works the same way. So let's take a look at that one. So this problem, we have e to the x cosine x dx. So we have e to the x instead of an x cubed term. And this causes a little bit of change, right? So whereas the x cubed component, when we defined it as u, went from x cubed to an x squared, e to the x, we know when we take the derivative of it, where is that? Right there, we get e to x again. When we take the integral of it, we get e to x again. So it's not going to change in that way. We know cosine is going to go from cosine to sine to cosine, and with sine with plus or minus changes. So how are we going to solve this one? So for this case in particular, it doesn't matter if you choose u to be e to x or u to be cosine x. What we're going to see is a repeating pattern. So this integral is going to show up in a different form and then repeat the same form. So that's not a very clear way of explaining it. So let's walk through this process in one method, and then I'll let you know that you can switch the u and dv definitions, and you can try that one on your own. Make sure that you get the same final solution. Okay, so for this case, just because we solved for dv as cosine x dx in the previous problem, we're going to keep it consistent here. Now, you can try in parallel to solve for it, defining cosine x as my u value and defining dv as e to x dx. You'll get to the final form. The last step, you'll see everything fall out, and you get the same final answer. Okay, so let's work with this method first, though. So if u is equal to ex, I know du is going to be ex dx because that's just the derivative right there, right? dv is cosine dx, so I need to take the integral of cosine, and that's just going to be sine. So du is ex dx, and my v is the integral of cosine, just sine x. All right, and then we can plug it into this equation here. So uv will be ex sine x minus integral of v du sine x e to x dx, right? So I don't know how to take the integral of this part, right? This red component here. So we're going to set it up in the same way that we set this one. So I'm going to define u as e to x again, and dv now is going to be sine x dx. And when we set this up, what we're going to find is that final form ex cosine x dx is going to show up again. And that's going to be how we're going to solve for this problem. So e to the x is going to be, du is going to be e to the x dx, and v is going to be the integral of sine x, would be negative cosine x. All right, so now I have u and du, dv, and v, and I can plug it back into this equation. So uv will be e to the x times negative cosine x minus integral of v du. V is negative cosine x du e to the x dx, and that's the same form as my original. So uv minus integral v du. Clean this up a bit, we get negative e to the x cosine x plus integral e to the x cosine x dx. Remember, this whole quantity here is this integral term here, which is equal to my original form. So let's plug that back in and let's compress all into a single equation. So what we're saying is this original e to the x cosine x dx, this one right here, is equal to the first part, e to the x sine x minus integral e to the x sine x dx. That's right there. This right here is equal to this component right here, right? That's what we saw for in this step. So I can plug that in. So e to the x sine x minus, now we're plugging in this right here, negative e to the x cosine x plus integral e to x cosine x dx, right? This is the original function we're trying to solve for. It shows up right here as well in an additive manner. So I can grab this term and move it over here. It has a negative sign in front of it, right? So if I distribute this through it, you see that as negative sign. So I can put it over here, and it'll be 2 times this function is equal to the rest of these terms. So 2 times integral of e to the x cosine x dx is equal to e to the x sine x, distribute the minus sign there, plus e to the x cosine x. So I can just divide by 2 and I have my final solution. So integral e to the x cosine x dx is equal to e to the x divided by 2 times sine x plus cosine x, and all of that plus c because the indefinite integral. Now, if you would like to practice this, try starting with this problem again and switching u to be defined as cosine x and dv as e to the x dx, and see if you can get that same final form. And you could do a lot of different iterations, right? You could do e to the x sine dx, right? So you could solve for this one as my ultimate. And so then in that case, you would start with this and you would take multiple steps again. So, you know, hopefully this makes sense of what you need to watch out for when choosing your u and dv substitutions. And you're either trying to decrease the complexity of your u term with this du component, or trying to find a pattern like we did in this one, where we see a repeating component, and we can do that final trick right here where we just do a substitution or manipulate this integral right back into the same final form. Okay, so we have one last property type of integration rule set, that video that we're going to do, and then we could do some application integral problems.